Welcome to Lab 4 for Physics 2211. Today we will be going over oscillations. In this lab we will discuss a preview of the results, the physics principles and an analysis in the context of the lab. We will analyze the principles and then we will go into the tracker data. Then I have used GlowScript to model and compute the other computations. In this lab, we will observe and compare the predicted model with our observed motion of the mass attached to the spring using tracker and GlowScript. We will see the changes in potential energy, in gravitational potential energy, spring potential energy, and total energy. We will find the model produced similar results in the x and y axis as the computational model. Some of the important forces that we will discuss include Newton's second law, the energy principle, and gravitational force. The energy principle states that energy can neither be created or destroyed, which is apparent in the formula. The Newton's second law affirms that an object in motion will remain in motion unless acted on by a force. Gravitational force pulls objects with mass towards each other, in our case, Earth. Some relevant formulas are energy displaced of the system will equal work done by the surroundings plus temperature, the momentum principle, the velocity change principle, kinetic energy, energy of the spring, energy of gravity, and net force. I've also constructed a free body diagram to better illustrate the static equilibrium position. In this diagram, we have made the system the spring, earth, and the mass, and the surroundings nothing. With nothing in the surroundings, we have a multi-object system. This is illustrated in the net force of the gravity and the spring equaling 0, so the equilibrium. Because we can see that the system is in equilibrium, we know that the total energy change is 0. So we know that the kinetic energy, the energy of the gravitational, and the spring energy will have to equal this. Then, putting the video into Tracker for better analysis, we were able to track the oscillations and the starting points and initial positions and velocities of the mass. The analysis from Tracker shows that our observations of the start time is 0 seconds, initial position is the following vector, along with initial velocity being the 0 vector. The stop time is approximately 6.34 seconds. The graphs shown here are the x and y positionings of the oscillation movements. Here is the code I put into GlowScript. There is changes made to the delta t, the ball.m, which is just the mass, the position vector, and the velocity vector. In the next one, I changed the spring constant and the relaxed length of the spring to reflect our video analysis. Then I computed the system's energies of kinetic energy, gravitational potential energy, spring energy, and total energy. Using those numbers, I was able to define initial energies and calculate the F gravity vector, the F spring vector, and the F net vector. Then we reiterated the ball velocity and the position update formula for the ball and completed the spring length with the ball position minus the spring position. Here we have the different gravitational potential energies alongside the kinetic energies, total energies, and spring energies. We can see these in our graphs from GlowScript, and here we have compared the outputs of our predicted model and our computational model. Some questions that we might have had are, is the energy principle satisfied in our demonstration? We can see clearly that the energy principle is satisfied. This is proven by our graph created by GlowScript and how it shares similarities with our graph created in Tracker. We can see that the total energy displaced is 0, which proves the equilibrium and the concept of oscillation in this case. The next question is, using the data we obtained in Tracker makes two separate estimates of the oscillation periods. To do this, I calculated the time that each oscillation in each direction took. So for the x direction, it took approximately 6.664 seconds, divided by 4 oscillations to get the 1.7 number, and in the y direction, approximately 7.322 seconds for 5 oscillations, giving the number 1.343. Some possible errors this lab may have had are tracking errors in the tracker and misrounded calculations in our computations. Thank you.